Hi everyone. So I was given chapter 9 on correlational research to look at and read. So I'm going to be giving you a little overview of what this chapter was about and what correlational research is. So research involves collecting data to determine if there's a relationship between two or more variables. We could just have two variables, but we will see one case later on where there could be three variables that we're looking at to see if there's a relationship between all three of those. And one of the main things that we need to look at when we're choosing our variables for research is that the variables that we're choosing have to be quantifiable. We have to be able to give these variables a score and test something from them. So if we're looking at categories, we're either assigning them 1 and 2, or we're giving something rank or doing ordinal kind of variables. So we're saying first place for something, second place, third place, and each of them being that first place is a higher value than second place, and so on. With this type of research in general, we're looking to have a sample size of at least 30 participants. There's one case later on we'll talk about potentially it might have less, but otherwise, like, this is very rare. We want at least 30 being the absolute smallest that we have, and anything greater than 30 would actually be much better. This study allows us to describe if these variables are related, but not if there's a cause and effect kind of relationship. So not saying this causes that or that causes something else to happen, but more just, is there a relationship between the two variables? One example of this, we're looking at how maybe your high school GPA might imply, predict, or relate to your GPA or your performance in college, but not so much how maybe your high school GPA affects what college you get into. So when we're doing research, and this is correlational research, we're determining either relationships or, like I just said, we're looking to make a prediction, looking at two variables and how one might predict or make a prediction about the other. And I said before that one of the most important things was looking to make sure our variables could be quantifiable or could be quantified, but really we should also be looking at these variables as we're selecting them based on theory or experience, some kind of idea to back up why we're selecting these variables, not just randomly choosing and looking to see how maybe dogs would predict or relate to people liking baseball. There's no theory on that. You might have a little experience, but it's not something we're looking to study. We want to choose variables that there's some kind of theory behind them, and determining if they're related or kind of predict something about the other would have an impact on either education or some kind of field. So with correlational research, we have this thing called a correlation coefficient, and this indicates the size and the direction of a relationship. This coefficient is a decimal number ranging from negative 1.00 to positive 1.00. And the negative and the positive, those itself don't represent how strong the relationship is. They represent the direction of the relationship. So in this first example up here, hold on. So in this top one right here that I just drew a circle on. So this one, we could say this would have a correlation coefficient of near positive 1.00, which means that these two variables, whatever they may be, let's call this one x and y, like we would normally see on a table or a graph. We're saying that x and y are strongly and positively related. So if we were to draw a so-called line of best fit, This would be a line that is super, super close to all of the points and could be described best from most of these points. Might look something like that. Right, all of the points are super close to the line. And this line would have a positive slope, or we could like walk uphill, walk up the mountain that our line has created. And our line is straight and all of the points are close. So the closer the points are to this line of best fit that I could potentially create, the stronger my relationship is. The positive part comes in by saying as x increases, or as x goes from 0 to 5 to 10 to 15 and so on and so forth, y is also increasing. So I'm starting at maybe this point here is like 445, and all of my points are following a similar trend until I get to maybe this point at the end that we could describe as maybe 27 and 180. All right, so the next one, which could be this one on the bottom. Oh, no, hold on. I skipped forward. Sorry. So the next one could be this one on the side. This one, if we drew this line of best fit, it might look something like that. All right, so all of the points are super close to the line. They're all kind of following the same trend downward, but still sticking close to this line, so they're doing it kind of similarly. And this would have a correlation coefficient near negative 1.00. So it's strong because all of the points are close to this line, and it's negatively related. So again, if we're saying the bottom, we're calling it x, and the top, we're calling it y. This negative relation is saying that as my x is increasing, so going from 0, 5 to 10 to 15 to 20 and so on, my y is decreasing. So I'm starting at maybe this point with a y value of 180, and then each of my points after that following the same trend, and I'm ending up with a y value of maybe 60. Right, and like how we said, this first one was if you're walking uphill, and that's a positive relationship. My negative relationship could be described as walking downhill. And then finally, this last one, which I was jumping to beforehand, this last one right here, we could say that this would have a correlation coefficient near 0.00. So a very weak relationship. We can't exactly draw a line of best fit. And if we did, say it was that one, my points are like kind of close, but we have a few that are like way different. So we can't say that this has a strong relationship because the points aren't close to my line. So this would be a no relationship at all between my x and y, or a very weak relationship. And again, something important to point out is that my correlation coefficient, while it is a decimal number, it does not indicate a percent. So it's not saying my x and y are 75% related if I had a correlation coefficient of 0.75. And then, so a sample interpretation that the textbook had given was something like this. It was saying that between negative 0.35 and positive 0.35 would be a weak relation. And then from negative 0.35 to negative 1, we would have a strong negative relationship, and then a positive relationship for 0.35 to positive 1. But this was only a sample interpretation because, as I said down here, it depends on the type of test that we're taking. So if we're looking at an effective test, an achievement test, and then going on reliability, or if we're making the prediction or looking at a relationship, these sample interpretations could be different. And going back when we were talking about making that percent kind of connection between the correlation coefficient, and the relationship, we could take what's called the common variance, which is the extent that the variables vary, and we could take this based on the correlation coefficient and turn this into a percent, which I will talk about in 1 second. But this is telling us that if two variables are strongly related, so R, what we're typically going to see as the correlation coefficient, this R would be close to positive or negative 1.00, then the variabilities are similar. And so if we're using variance, we're saying this is V, and our correlation coefficient is R. Something mathematical, the way we can kind of connect these two, is by saying that our common variance V is equal to the correlation coefficient squared. And when we do this, say R was maybe 0.4 positive, and we could square this. Well, first, if we have 0.4, we could say this is generally a weak relationship, but it's positive, so something's increasing as something's increasing, but they're not too strongly related. So if we square this 0.4 to get our common variance, we would get 0.16. And then we could then go ahead and turn this 0.16 into 16%. So we could write variance as a percent, but we can't write correlation coefficient as a percent. So next we talked about statistical significance, which was the probability that the results would occur simply due to chance. And then right here, to be statistically significant, R must reflect a true statistical relationship and could be weak or strong, but we're saying it couldn't have occurred just due to chance. So if this probability is low, we're looking at a true relation or something that's probably not due to chance. And when we're looking at this, we're saying that 0.05 is the cutoff point for our probability, which tells us that the smaller our probability is, the more confidence that we have true results. So then we looked at two different types of studies, either a relationship study or later we'll talk about predicting. So relationship, we're collecting data, we're identifying variables, and we're looking at an appropriate population to sample from. And it's really important when we're analyzing this data, we're determining a method for computing the correlation coefficient, because right here we can see that there are quite a few different ones. So the Pearson R, that's the R we were just talking about, and that's appropriate for using continuous kinds of data. We have Spearman-Rao, which is if we're talking rank or ordinal, and then a few others. But mostly, these are telling us we have a linear or straight line relationship. But there's also curvilinear relation, which is saying like how a car depreciates in value when you first, but then after years and years, like when it's an antique, people will want it more, so it'll become more expensive. So this is kind of the characterization here. So next we have what is called a prediction study. Sorry about that. We have a predictor, which is a variable that is used to predict, and then a criterion, a variable that is predicted. And then predictor variables are obtained before criterion variables. When we're analyzing the data that we get from these studies, we're using the formula y equals a plus bx, and here's what each of those variables would stand for. So some problems to consider when we choose the proper correlation methods to use, that's definitely one. Reliability, validity, and sample sizes. And then an intervening variable, or a variable that alters the relationship of the variables that we're studying, and we can't always control it. So next up, we have the real-world example study that we were looking at. And this study had the purpose of determining the relationship between reading achievement and parental involvement. So it had 48 participants, and then we're using the correlation coefficient R. So our variables, we're looking at parent participation in their child's education, which is our independent or our X variable, and then reading level, which is our dependent variable or our Y variable. So we looked at the results of this study. We found that we had a Pearson R, or a correlation coefficient R, of 0.0129. And we could use this R because the variables were both continuous. And this R told us that we had a very slight positive correlation, but the correlation or the relationship with these was very weak. They were very close to that 0.00, which means that we failed to reject our null hypothesis, which was that there was no relationship between the two variables. Also with this, it's not statistically significant because there are those other extraneous or kind of variables that it's hard to track